we are recording. So welcome everybody to the third talk of the online seminar series called Tunneling in QFT, where we explore topics related to false vacuum decay, phase transition, nucleation rates, and other related phenomena in QFT. So these talks take place roughly once a month, and the two previous talks were given by Ian Moss and Sylvia Pla, and you can check them out online on the YouTube channel. The next talk will be on April 18th. It will be given by Patrick Draper. And today we have our speaker, Yutaro Shoji, who is a postdoc at the Jožef Stefan Institute here in Ljubljana. And he's been working on the topic of false vacuum decay for quite some time now, a couple of years with his collaborators. In particular, they made some significant progress on establishing the gauge invariance of such transitions in the standard model and also beyond in BSM theories. And today he will tell us more about this particular issue, about gauge invariance and the existence of gauge zero modes in bubble nucleation. So as always, feel free to interrupt and ask questions. The talk will be roughly 1 hour or so. So Yutaro, please start.
Thank you, Mihar, and then thank you for coming. So today I'd like to talk about some kind of theoretical development of some calculation of the determinant, especially of the determinant of the gauge sector. And then there are three theory papers listed here, and also we also did some applications, including the standard model calculation, and we actually updated recently. And this is the kind of the standard model, a stability, and then we are still in the metastability. I will come back to this slide. That's this figure in the very last slide. So let me start with the introduction. Probably you already kind of the first lecture is about this kind of formulation, so you already know this formula, but just to recap whatever I need. This is the bubble nucleation rate in the unit volume, and then this is by Callan and Coleman. This is written in this form, and this exponential suppression factor is basically the action of the bounce. And the bounce is the orthosymmetric solution of the equation of motion. It's Euclidean equation of motion, just connecting this false vacuum to somewhere the exit point. And there are many programs, fine bounce or Cosmo transitions, and also that we have developed some algorithm to obtain this kind of bounce. And then actually this calculation is rather kind of easier than this prefactor calculation. And then for the prefactor, this basically determines the overall factor, and also this has a dimension. So we just needed to fix this prefactor. And this is basically the quantum correction, the one loop quantum correction to the action. And this is basically all the fields coupling to the bounce contribute to this determinant. And then actually there are several zero modes. That is typically we have translational invariance in the space, because this bounce is localized object, so you can just translate the time direction or space direction. Then actually that is the flat direction, so we have the zero mode, or just the second derivative is zero. So we have to subtract these zero modes, and then also we kind of use multiply the Jacobian for for example, translation of zero mode, and just this is just Jacobian for that. And then we have to multiply the volume of the moduli space. But for the translational zero mode, we just do not need to multiply the volume, because we are kind of already divided by the volume of the space and the time. So, but if there is a flat direction in the group or the gauge symmetry, then there appears also the zero modes, and we have to kind of subtract from the determinant and multiply the Jacobian and multiply the volume of the group that is broken by the bounds. So that is the general procedure to calculate the nucleation rate or the vacuum decay rate. And then actually for the prefactor, actually in the many the papers, they just put some random typical scale in the front, because it's in the 4D, this has the dimension 4, mass dimension 4. So just you can just put some typical scale to the force, then just calculate the exponential factor. But actually, it's not a very good approximation, because, for example, in the standard model case, I just give a rough picture of how large it is, and this if the decay rate is basically the kind of the integral of this region, and so actually the and the bottom figure I just plotted the quantum correction from the various field in the standard model. And so the important region is here, so that we can just read off what the value of this prefactor from D, W Higgs on top. And actually, it's kind of exponential 50 to 100. It's a kind of a very large correction coming from the loops. So even if you set some typical scale to the force, but exponential 100 difference from the typical scale is kind of random scale. So that's why we have to care about this prefactor, and also that we have to compare this value with the Hubble to the force, because this is basically the size of the universe and then the age of the universe. So in order to have our vacuum until now, we have to make sure that this value is smaller than an exponential 400. But this is already 100, so actually this matters a lot. So that is why we have to kind of calculate the prefactor. And then our today's topic is about this gauge boson contributions. So that's the introduction. And then I will next show the gauge invariance of this determinant. And then I will go to the case where there's a gauge zero mode. And then there's a special case that the Fubini instant on this the bound solution, and then actually we have to treat this separately. And then everything is now generalized to multi-field bounds. And then now finally we can just I can just show some phenomenological applications that we have done, and then summarize. So to discuss the gauge independence, probably we have to start with a very simple case, because otherwise it's very complicated. So this is probably the simplest case. So this is one complex scalar phi, and then gauge boson A is here. And potential looks like this. Actually, this potential cannot be made with renormalizable terms, but actually we don't care about the renormalizability for the moment, because it's basically we are only calculating one loop and just put the counter term. So for the theoretical point of view, it's okay to put some non-renormalizable terms. So just let me just assume that the potential looks like this, and then we have to gauge fix otherwise it's just have lots of zero modes, and there's a problem. So we have to fix the gauge. And then actually there are two gauges that we use. And then one is the arc psi gauge in the broken phase that usually you use in the broken phase. That is we call the background gauge, because we also have some other another arc-side gauge that we usually use in the symmetric phase. That's we do not have this thing in the gauge fixing term, and then the ghost is trivial for the U1 and in the Fermi gauge. So actually, this Fermi gauge becomes important later on, but just let me go on. So what we want to calculate is the functional determinant around the bound solution. And the bound solution is in the 4D, it's all for symmetric. So it's very good to expand the fluctuations with hyperspherical functions. This is basically the spherical function in the 4D. And then for the low-length scalars, it's, for example, the fluctuation towards the bound solution where the imaginary direction is all a scalar, so we can just expand with the hyperspherical functions. And then, of course, the Faddeev-Popov ghost is also the scalar, so we can just expand with the same functions. And then the vector we have to prepare for, say, the independent basis sets. And one is just the x mu over r. R is the modulus of x. So it's basically the vector pointing outwards. And this derivative mu of this one is just a kind of 1 over the angular direction. And the other ones are just can be made from some outer product of these two vectors. So this is some outer product of their mu and the x mu. And then we know there are two independent vectors. So just we multiply this with mu. 1 and 2, these are just random independent vectors. Then we can just construct these 4 basis sets. And then actually when we calculate the determinant for the on the bounce background, something unusual thing happens. That is, basically this the Nambu-Gostan mode and then this vector wasn't just mixed with each other. Just it cannot be kind of separated. So that makes things very much complicated. And actually, it looks like this. So this is SL is the two modes in the gauge sector. A is the Nambu-Gostan mode, and this A and S for L equals 0, just mixed with each other. And then there is no mixing between different L's, but yeah, for L larger than 1, actually SL and then A just mix with each other. So it's kind of very complicated matrix. And this is the Faddeev-Popov ghost. We have also psi dependence here. And T1, T2 is the other gauge modes, and this is kind of a physical mode. And then there's no psi here. So actually, in the actual numerical calculations, the background gauge and the cycle 1 is very good, very useful gauge, because if you take this equals to 1, then we do not have this last line, this very complicated line. And then actually off diagonal part is like these two, but these two are kind of, if you go to R equals L, this is the center of the bounce, or the R equals infinity, that is the false vacuum, then this psi of, phi bar, the bounce is 0. So this decouples from this part, and this, this gauge boson part actually can be diagonalizable. That is diagonalizable. So that's actually, this makes the calculation very, very kind of easier. So that this is very kind of useful gauge. But on the other hand, the Fermi gauge is much complicated, because we cannot cancel any of the off-diagonal part of the gauge boson and the Gauss-Stone boson. So we have fully, mixed with this. They're fully mixed, and then on the other hand, this Faddeev-Popov gauge, Faddeev-Popov ghost is very trivial. And then this T1, T2, the state the same as before. So this is the gauge and how it looks like. And then actually what I want to show is the gauge independence of this object. Actually, this Higgs mode, it's just this is apparently a physical model, nothing to do with the gauge. So this is gauge independent. And the T, as I said, this the fluctuation matrix is psi independent. So these two are manifestly gauge independent. However, Faddeev-Popov ghost for the background gauge, this has the psi dependence here, and this SLA fluctuation, for example, has psi dependence here and here. It's kind of very complicated matrix, and then we cannot easily see that these are the gauge dependent, but of course it should cancel because otherwise it's not a physical quantity. But that is not very clear from this formula. And actually, there are several related works that basically, in principle, can be shown can show that is the gauge invariant. One is so-called Nielsen identity. That is often people use for the effective potential. And then that's basically saying that if you change the gauge parameter, then if you change the gauge parameter, then the position of the wave also changes depending on this psi. So if you change this wave according to this psi, so that it is always the extreme of the potential, then the height of this potential is gauge independent. That is the Nielsen's identity. And then it should be kind of applicable to saddle point for the effective action. But actually, it's not direct proof, and there are many kind of complications. And then there's also a problem that of course the quantity may be gauge independent, but it actually doesn't tell us anything about how we should treat the gauge zero mode. So this is kind of one thing. And then there's another way to show the gauge invariance. This is more like explicit way. That is just actually using the so-called Gelfand-Yago theorem that I'll explain later. But what they did is just that they found one Faddeev-Popov determinant in the gauge determinant, but actually they only found one, and we need another Faddeev-Popov determinant to cancel all of the gauge dependence. But actually, their discussion kind of hand waving. There's probably there's another Faddeev-Popov determinant, and actually they didn't kind of provide the complete proof that actually we needed to do it. That is kind of an asymptotic analysis of this Gelfand-Yago theorem, but actually it's not provided. So that's so, and also they just assume that there is no gauge zero model. So actually our work is kind of along this line and kind of completing what they wanted to do. So just let me explain what the Gelfand-Yago theorem is. And this is kind of interesting theory that this determinant of the second derivative operator is related to some solution of the ordinary equations, differential equations. And then this SLA written here is a 3x3 matrix of the second derivative operator. And what we do is that actually, if you multiply this 3x3 matrix to three vector, then this gives the second order, simultaneous equation of three equations. And so we have 6 independent solutions. But the 3 of them are singular at the origin, so we just take 3 independent solutions that are regular at the origin. Then we have 3 vectors, and also these are that, I mean, 3. This is 3 by 3 matrix, so we can just take ordinary determinant, and we can do the same for this M hat. This is the false vacuum determinant, and we can also do the same thing and take a double ratio, and that gives exactly the determinant of these operators. That is kind of a very non-trivial statement. And then there are many proofs in the mathematical papers, or even some physics papers. And also, we also provided some proof in our paper, because this M is a kind of special matrix that is not, I mean, cannot be directly proved by the other papers. But yeah, this just gives some general procedure to just show this one. So if you are interested, then you can just look at this one. So actually, using this theorem, what we have found is the following. So this is the first case is where there is no gauge zero mode. So that means that the gauge symmetry is already broken at the false vacuum. So at the false vacuum, the gauge boson is massive, and then that's also the Tool vacuum is probably massive. And that in that case, actually we can calculate this determinant using this theorem, and also doing some asymptotic analysis of this determinant. And we found that actually this, I mean, this is just given by the this solution. This is just this Kelpan-Diagon theorem. But if you calculate this 2 by 2, this is 2 by 2 determinant, this is 3 by 3. And then what we get is actually, if you calculate, then this gives the same factor, I mean, factor as in the Faddeev-Popov determinant, multiplied by the wave at the false vacuum over the wave at the center of the bubble. And also we can calculate this 3 by 3. Then what we get is also it's written by the value of the bounce and the Faddeev-Popov contribution squared, and then this physical mode. This doesn't include any psi dependence. So that means that actually, if you calculate the whole of the prefactor, then in the prefactor there is a determinant of this one, and the square root of inverse of this determinant is in the prefactor. So this Faddeev-Popov contribution cancels completely, so that the prefactor becomes gauge independent. And for the Fermi gauge, actually the same thing can be done. And the Faddeev-Popov determinant is trivial. It doesn't give anything. And then this SA mode, even though these metrics have psi dependence, but the final result is the gauge independent in this, even in this combination. So, and then this one is also gauge independent. And then we can show that you can see that actually this background gauge and the Fermi gauge just agrees very well after this multiplying everything. Yeah, that is how we showed the gauge independence of this determinant. And the problem is that there is when there is a gauge zero mode. This happens when the gauge boson mass is 0 at the false vacuum. When it happens, then we can kind of breaking the symmetry. Actually, it's a global part of the gauge symmetry by the bound solution. So there appears a flat reaction, and then if you use the background gauge, then this introduces the mass term for the gauge boson, I mean the number boson mode. So if this mass term just tilt the potential, so that here there is no zero mode in within this scalar potential, but still there is a zero mode. Actually, if you calculate this, I mean, put this in the right and just multiply this, and then you can just easily show that this is exactly the zero mode. FCC is something, some function of some solution of differential equation. And that means that actually this is the gauge boson direction, and this is the phi direction. And that means that actually if you move towards this zero mode, then this symmetry is very kind of non-trivial, that the phi becomes something very strange function. And also A becomes, the A has to have a wave if you go to the flat direction. So it's very, even though this probably gives the, gauge independent result if you, integrate over all the flat directions and come back to the original position, then probably the whole thing should be gauge independent. But here we cannot say anything because now if you go to the flat direction, then everything changes. Even this functional determinant have a different form because now gauge boson has the verb. But for the Fermi gauge, this doesn't happen because we do not introduce any mass term for the Navier-Stokes mode. So actually, the flat direction stays flat direction. So the global symmetry is very trivial. And then if you go to the different and move towards the flat direction, but still this functional determinant stays the same, so that we can just simply multiply 2 pi and then the Jacobian. Then you can just integrate over this flat direction. So that is the good point of the Fermi gauge. And then good, as I told you, that the good thing in the background gauge is that it is very useful for the computation and numerical computation. So what we did is that actually, because we know how to do it in the Fermi gauge, and we actually know the relation between the background gauge and the Fermi gauge, then just to use this result to find out what VG and JG we should use if you calculate in the background gauge. That is what we have done. And then actually we can do the same analysis for this case, and actually the result is a bit different because now symmetry is restored, so that actually asymptotic behaviors are a bit different. But the structure is very similar because we have this Faddeev-Popov mode appearing in the gauge determinant in the square, so they should cancel out. But the problem is that now we have a difference between the background gauge and the Fermi gauge. Now, just ignoring this red part, and this is 1 trivially. But now here, if after subtraction of the zero mode, we have JG here. JG is some function of this one, or just a number here. And then actually here, we have a different factor here. And this is gauge dependent. And then these are the same. So if you subtract the zero mode, then this determinant depends on psi, and this doesn't. And this is okay because if you subtract zero mode in the Fermi gauge, then you can just simply integrate over this flat direction. So this should be gauge independent, and it is independent. So it is okay. But here we have to kind of integrate over very non-trivial flat direction. So even this is, say, gauge dependent, it actually doesn't say that the final result is gauge independent or dependent. So actually, then what we can do is that instead of doing this non-trivial integration, just calculate the Fermi gauge result from the background gauge, then just integrate over this, multiply this 2 pi, then actually the calculation itself is kind of can be done. So that's translation is just like this. So the prefactor has the gauge volume times Jacobian times this gauge boson contribution times the Faddeev-Popov. And if you calculate in the film gauge, this is very kind of has a simple form here. And if you calculate the background gauge, I don't know what the Jacobian for the gauge, the background gauge, but in order to match these two results, actually we can just derive what Jacobian we should use. So this is the Jacobian for the background gauge. And then this actually how it behaves. The background gauge is just actually this Jacobian is psi dependent. And what we calculate is on the psi code 1. So that's how we can solve this Jacobian problem. And there is another benefit of this calculation, because now we can fully use the background gauge with cycle 1, and then the prefactor looks like this. So this is just the functional determinant for the Higgs model. So this is always there, so we can just ignore for the moment. And for the gauge sector, as I said, this transverse mode and then this Faddeev-Popov mode actually cancels kind of accidentally, because they have the same, I should show that. They actually have the same form, but when we take cycle 1, then they are kind of the same operators, so just accidentally. So we can just fully make use of it, and they just cancel out. And then actually for this part, actually we know the analytic result. This is just given by the value of the bounce at the center and the false vacuum. And also this, even with the gauge zero mode, actually we know that it's analytically, except for this bounce. And then this f is actually the Bessel function we can calculate analytically. So only the information is the bounce. We can basically get these values analytically. So then what we only needed to calculate is just this determinant from L equal 1 to infinity. So that's actually reduced the computational time very much. That is the case for the case where the potential have two minima. And there is another very special case, and that is important for the standard model calculation, is that the potential is just given by the quartic. Then this lambda is, when this lambda is negative, then potential looks like this. And then actually the decay can happen from this top of the potential to anywhere, actually. And this bounce is given by the so-called Fubini instanton. And this have the arbitrary constant R, because this is kind of a scale invariant at the classical level, so that any sides of the bounce contribute to the decay rate at the same level. So if you calculate the decay rate, we have to integrate over this sides of the bubble, and then we have set the prefactor. Now, because we have the flat direction towards this R, change of the R, so we have to also subtract the dilatation zero mode and multiply this Jacobian, but this is basically the same. And we also have the gauge zero mode because we start from the center of this potential, so where the gauge bottom is massless. But fortunately, like Harvard group and we did, actually we can calculate the determinant analytically. So we even do not need to go to the background gauge. We can do everything in the Fermi gauge, and then we can calculate this determinant explicitly. That is a very good point. And actually you can easily see that everything is gauge independent. There is no psi parameter entering this formula. So that is the single field case. And then I go to the merge field. that is a little bit more complicated, but just to show that the way that we have developed can be extended to any number of bounce fields. So this is just a rough sketch of the calculation, but anyway, if you have some bounce, I mean, the potential with many fields, and the bounce is kind of not single field, but kind of carving in the field of space, then just bring such a scalar field and put in the vector, and these are the real scalars. So if you have the complex scalar, just divide it into two and just put in the vector, and all of these I mean generators can be say put in the SON operator of large N, and you can embed any compact group into this representation, so that basically this TA is just generator satisfying this one, and this M transpose M defined by this is basically a gauge boson mass matrix. So this is the and we have because we have many scalar fields, so we have to kind of divide into two classes. One is the massive at the false vacuum, so there is no zero mode here, and the other ones are massless at the false vacuum. So for these, we have zero modes. So zero modes are kind of related to symmetries of the action, and that is only broken by the bounce, and it's not broken in the false vacuum. And then actually we this TA is a part of this zero, the flat direction, but we just take a linear combination for some reason. I'll explain later, and that is we call TA tilde. And also we could have some global symmetry breaking that is not the gauge symmetry part, and that is also we can have in the as a symmetry, and it may be broken by the bounce. And why we kind of take a linear combination is that we have to kind of make sure that this Nambu-Goldstone mode are orthogonal with each other. Otherwise, we cannot kind of trivially integrate over the group volume. And probably the gauge boson and then Nambu-Goldstone model, we usually take it to be orthogonal. This is kind of automatic, but within the Goldstone mode, and then within the gauge boson would be Nambu-Goldstone boson, we have to take kind of orthogonal basis. And then what we need is only the Jacobian for the background gauge, because we want to calculate everything in the background gauge. And if you know the Jacobian, then we can do all the calculation of the gauge sector. So this is the result. So you can have just calculate this one, and then you can just put in front of the determinant, and everything is okay. So this is from the global symmetry. This is kind of known from the very beginning. But the new part is this gauge symmetry part. If we break the gauge symmetry, then what comes in this determinant is just given by this one. You can just calculate this equation, differential equation, just to solve this. This is kind of have the same number of gauge bosons, so it's kind of n by n matrix. Then you can just solve it and then take a determinant, and that is the determinant for the gauge and the Jacobian for the gauge. The one thing that is we have to make sure, we have to be careful is that the volume of the flat direction should be measured with this TA or T to the alpha that we defined to calculate this determinant. This is kind of the measure of this flat the moduli. And if you take a different basis, then you kind of the volume you have to multiply is different. So if you say that say SU2 volume is 16 pi squared, but it may be 2 pi squared depending on the normalization of the generators. So that is the one caveat. So this is the multi-field, but for the Fubini instanton, this is much more much simpler. Actually, this is the case where we have only quartic potential, so there's no dimension flow parameters, or approximately there's no dimension flow parameters. And then we actually take renormalization scale to be 1 over R for some other reason. And then actually what we have to do is just we just find the steepest direction of this lambda, the quartic potential, and then just use the single field result. That is kind of very simple, and it's kind of very intuitive. And then proof itself is given in this paper. And if there is a case that there is more than one coupling that have the same order and the negative, then in that case we can just add all of the decay rate, and that is how we do it. So that's basically the how to do it. And then we actually applied it to many, not many, but several phenomenological models. One is, of course, the most important one is the standard model. And then actually the Harvard group, and we actually did in almost the same time. And then actually, recently the particle data group data are kind of updated. So we just replotted the this instability diagram with different alpha s and then different contours. And then this is the current best fit value of the vacuum decay rate, just assuming that the standard model is valid up to Planck scale. And actually, as you can see that this from 2017, this the error just shrinks very much, and the central value just shifted to the stable direction. So probably it's better for us, or maybe not. And then actually, if the bound solution is Fubini instanton, then we can do, any models. Like you can add the vector-like quarks, vector-like leptons, or right-handed neutrinos. Then that is a fermion, so it makes the running of the quartic coupling more kind of going to the negative direction. So actually this makes potential unstable, so that actually we can apply it to these models if it just changes the RG running. And we also apply it to two Higgs-Tablet models. So now we have two direction that can be unstable, and just we actually did some analysis. I don't go into details of these models, but the one thing that I just advertise is that everything is written in the analytic formula, so that actually if you write a code that is just copy and paste from the paper, then you can just calculate any determinant for the Fubini instanton, but it's a very lengthy formula, so we already coded in a public code. So if you want to use the analytic result in our paper, then you can just use this code, and you don't need to type by yourself. And this is the most kind of extreme, it's the most kind of difficult calculation is just we tried is this one. This is multi-field bounce. The bounce is not a single, just curving in the field space, and there is also gauge zero mode. And this happens like in the supersymmetric model. This is we just added the B nodes and leptons to the standard model. So that is basically we wanted to explain the mu and G minus 2 anomaly. That is kind of if you have a B nodes and the leptons or the muons, then this is the coupling between the Higgs and the leptons. And yeah, then actually this kind of explain the mu and G minus 2. Then because we have this 3-point coupling, then if we want to explain the mu and G minus 2 with heavier leptons or heavier B nodes, then actually we need a large flipping term or the large trilinear coupling. And that means that this direction becomes unstable. And this direction can be muon or tau. It depends on what generation you put in the theory. So, but we just did both muon case and the tau case. And the prefactor is a bit complicated. And then this 3x3 means that this scalar have 3x3 matrix of determinant, and this is 4x4, this is 7x7, and this also has a gauge zero mode because this breaks the U1 electromagnetic symmetry because muon now has a bev. And the fermions we just had the top and the p node and the leptons, and there can be some other generations if they are light. And this is one of the results that probably interesting one is this one. This is just a case where only the muon is light. And then this just shows that the contour plot for one loop calculation, that is what we did, just to calculate the prefactor and the exponent factor. And this tree means that this A prefactor will just approximate it with the wave at the false vacuum to the false. So this is we call a tree. And then actually this is a contour plot that basically constrains the parameter space. Or this is just a plot of the the exponent or just the decay rate of the log. So this should be larger than 300 to 400 to be consistent with the current universe. So the constraint comes in between somewhere between the red and the blue line. And as you can see that this blue line and the red dot dashed line is kind of comes around the same place. That means that actually the quantum correction is around 100, even though we are trying to put the constraint around 400. So it's kind of a very big contribution, and it just changes the constraint by say 50 GeV for the muon mass. It may be not very big, but still we can see it kind of the difference is still visible. Now, just let me summarize. So the precise determination of the vacuum decay rate, it also, of course, depends on what precision you need for and what you want to see. But still very important for the precise determination. And then, of course, the gauge bosons are also has a very large contribution. And then before our paper, actually, probably people believe that the prefactor is gauge independent, but there is no kind of clear proof or some explicit proof of the gauge invariance, so that we actually provided. And then also we provided some prescription to treat the gauge zero mode that actually enables the computation of the gauge determinant for any kind of potential, even with any number of scalar fields. So and we applied this to several models, and then yeah, that's what we have done. So thank you very much.
Thank you, Yutaro, for this nice overview of your work. Do we have some questions from the audience? Maybe I go first. So you mentioned that there was a significant reduction of uncertainties from 2017. Can you comment a bit more on that? What was
This is the
reason that uncertainty goes down?
No, this is experimentally the uncertainty from the top mass and the Higgs mass, the pole mass and then MS.
Mm-hmm.
And then actually this contour is just the contour of the MT and MH. So just it's reduced because the experimental data is updated. And also the we just plotted central value of MS that is changed from 2017. So that's this line is slightly different. If you see this corner, then this start with exactly around the corner, but it's slightly off. So, but yeah, that is actually alpha is the largest error.
Maybe just one more question. The procedure that you were discussing doesn't depend on, like in the multi-field, whether the bounds goes from broken to broken or from unbroken to broken, or does it?
Actually, that's all included. I mean, this is, say, we already, separated, the broken, or it's, say, partially, we started from the partially broken. So some of the symmetries are broken and some are not broken. So and this is very general.
I see. Okay. Good.
Yes.
I think Oli raised his hand, so go ahead.
Hi, Yutaro.
Hi.
Mostly, I just wanted to say that was a very clear talk and very impressive work. And thanks. Very, very nice to see your talk. Actually, well, that was basically what I wanted to say. I did have a question though on this slide. You didn't explain exactly what was going on with this det kappa GA squared object.
Yeah, actually, this G, the kappa G, it's rather, it's say,
I mean, sorry, on the right-hand side, you have this small g,
right.
And then a squared, and then you have det kappa with no indices.
So this is just a separated determinant kappa, and this determinant kappa comes from this change of the basis. Or basically, we are just making this numbers more orthogonal with each other, and then we just have kappa here. And that appears here because we are basically kind of multiplying the gauge volume, but we have to make sure that the measure is kind of orthogonal to each other. That is just the determinant kappa here. And this determinant large K is a bit complicated, but still you can solve this one. And this AB is a sub-component of this fuller matrix. This is originally NB plus NU.
Okay, so these are the remaining
remaining
matrices.
AB. Then take this sub-determinant that comes here. And this GA is just the gauge coupling.
Thanks. Actually, now I have you. Can I ask one more question? Which is, so it seemed to some extent that you had proven the equivalence of this Fermi gauge and background gauge calculations. Then at some points you said you kind of used their equivalence to calculate some results. Right. So in your opinion, to what extent do you think you've fully proved their equivalence, or?
Actually, for this part, when there is a gauge zero mode, then actually the proof of this I mean, equivalence of these two gauge is kind of very complicated. Probably someone can do, but we just didn't show this explicitly, just assume that they are kind of the same, or they actually, we should say that we are kind of calculating everything in the Fermi gauge, then it should be okay, because this is apparently gauge independent. And our strategy is that actually we calculate everything in the backplane gauge, but I mean, transform this to the Fermi gauge. I mean, this just convert this to the Fermi gauge result. That is what we are actually doing.
Okay, thanks.
Okay. Andreas had a question. Go ahead.
Yeah, thank you, Yutaro, for a nice talk. Maybe I can ask something in similar spirit to Ollie. So let's say you wouldn't have any gauge fixing term explicitly in Lagrangian at all, but rather you would just impose some gauge conditions on your fields, like you would do for Svellerons, for example. Do you have like any sense if everything would work out the same way, or like how the results would be related to themselves in the end? Like, would there be like any subtle things?
So just I couldn't understand that. But,
Oh, so I mean, like for Svellerons, you don't add a gauge fixing term usually. So what you do instead, you impose some physical gauge fixing, you expose some gauge conditions on your fields, and that's it. You just add all fluctuations that satisfy that gauge fixing. So you wouldn't get the NG parameter. So in that case, would you imagine that much things would change in your derivation, or like it will be quite similar?
I haven't tried, so I actually do not know. But... Yeah, let me think. I don't know. I mean, if we do not have say the gauge fixing, then let it free and calculate the determinant. And I suspect that there should be an infinite number of zero modes. And
Is Andreas, Andreas, are you suggesting that you don't write a gauge fixing term, but you only do the determinants for the physical degrees of freedom, something like that?
Yeah, exactly.
yeah. Yeah, probably we can reduce gauge degrees of freedom by hand without using the Faddeev-Popov. Maybe, I don't know. It's I haven't tried, so.
Okay, thank you. I was curious if you already knew like how it would work out.
Yeah.
But thanks again for your nice talk.
Thanks.
Oh, Johan has a question. Go ahead.
Yeah, thanks. Yeah, that was a very nice talk. I guess I have a kind of conceptual question. Because if you just think about minima in the effective potential, then you have this kind of very nice you have this very nice accounting of degrees of freedom you can make. Like, okay, in the symmetric minimum, I have the gauge boson is massless and it only has these two physical modes. But then in the broken minimum, people use this language that it eats the Goldstone mode, and then it has three modes. But like with what you're doing now, and when you do these bounds calculations, then you are kind of in between these, right? Like, and I guess
kind of, yes.
I guess that's why it's so complicated.
Right.
Yeah. Like, I was wondering if you have any like physical way of thinking about it. Like, okay, yes, these do have to cancel because of gauge invariance. Like we expect it to be physical, but is there like, can you account for the modes somehow? Like, just curious.
Yeah, actually, it's Yeah, kind of if you take say the cycle infinity, then probably it's like a unitary gauge.
Right.
Yeah, it's looks like this kind of decoupling, but in the determinant, I don't know what's. A bit complicated because here there is one more xi, and then actually it makes this derivative to 0, so it's like,
Right.
yeah, it's, I don't know what will happen, but yeah,
Yep.
maybe it's
Yes.
good to think about it.
Okay.
Very good. So thank you everybody for your interest. Just to remind you, the next talk will be on April 18th by Patrick Draper. So I hope to see you there. So thank you, Yutaro, again for your very nice talk and for the discussion.